Section 23.2. Electric flux. In this presentation, we will explore the fundamental concept of electric flux, which is essential for understanding how electric fields interact with surfaces. We will begin by establishing a conceptual definition of electric flux, and see how it applies to both uniform and non-uniform electric fields across different geometries. Following that, we will examine the rules and sign conventions for calculating electric flux through closed continuous surfaces, such as spheres or rectangular boxes. Finally, we will discuss the physical interpretation of net flux, and what the total number of field lines entering or leaving a surface tells us about the enclosed system. To understand electric flux, recall that electric field lines help us represent the field quantitatively. The number of field lines passing through a given unit area is directly proportional to the magnitude of the electric field. We define electric flux as the product of the electric field magnitude and the surface area that is perpendicular to that field. Mathematically, this is expressed as flux equals the electric field times the area. The standard international unit for measuring electric flux is the Newton meter squared per coulomb. When a surface is tilted and no longer perpendicular to the electric field, the flux passing through it is reduced. For a surface area held at an angle theta to the field, the effective area becomes the area times the cosine of theta. It is important to note that the angle theta is measured between the electric field vector and the normal, or perpendicular, line to the surface. The formula then becomes flux equals the electric field times the area times the cosine of the canta. Flux reaches its maximum when the angle is 0 degrees, meaning the surface is exactly perpendicular to the field. Conversely, the flux is 0 when the angle is 90 degrees, meaning the surface is completely parallel to the field lines. In real-world scenarios, we often deal with non-uniform electric fields or curved surfaces. To calculate the flux here, we must divide the total surface into very small area elements. Each small element is assigned an area vector that points in the normal direction, directly away from the surface. The total electric flux is then found by taking the surface integral of the electric field dot product with the differential area vector. Ultimately, the total flux depends entirely on the specific pattern of the electric field and the exact shape and orientation of the surface chosen. Let us visualize this with a curved surface placed in an electric field. Consider an area element on the right side where the field lines are exiting the surface. Here, the angle between the normal vector and the electric field is less than 90 degrees, making the electric flux positive. Now look at an element at the bottom, where the field lines simply skim along the surface. The angle is exactly 90 degrees, so the flux through this specific element is 0. Finally, on the left side, where the field lines enter the surface, the angle is greater than 90 degrees, which results in a negative electric flux. This brings us to an important sign convention for flux through closed surfaces, like a sphere or a box. Flux is considered positive when field lines cross from the inside to the outside. Flux is 0 when field lines simply graze the surface. Flux is negative when field lines cross from the outside to the inside of the enclosed volume. To find the net flux, we evaluate the integral of the normal component of the electric field over the entire closed surface. This net flux is proportional to the net number of lines leaving the surface, which is the number of lines leaving minus the number of lines entering. Let us look at an example to calculate the net flux through a cube placed in a uniform electric field pointing in the positive x direction. For the four faces of the cube that are parallel to the field, including the top, bottom, front, and back, the dot product of the field and the area vector is 0, so they contribute no flux. On the left face, the field points inward, while the area vector points outward, creating a 180-degree angle and a negative flux equal to negative E times the length squared. On the right face, both the field and the area vector point outward, giving a 0-degree angle and A positive flux equal to positive E times the length squared. Adding these together, the net flux through the entire cube is exactly 0. To summarize, electric flux is a measure of the flow of the electric field through a specific area. It is a scalar, not a vector, and is defined by the dot product of the electric field vector and the area vector. When dealing with closed surfaces, we conventionally define the direction of the area vector to point outward. As we saw in our cube example, the net flux through any closed surface placed in uniform electric field, assuming it encloses no charge, will always be exactly 0. Before we conclude this section, please take a moment to reflect on 2 important review questions to test your understanding. First, consider why the electric flux through a surface is mathematically and conceptually exactly 0 when the electric field lines run perfectly parallel to that surface. Second, think about a closed surface where you have calculated a positive net flux. What does this positive net value physically imply about the balance between the electric field lines entering the surface and the field lines leaving it? Think about how this relates to the sign conventions we just discussed.